Introduction to Linear Programming Through Real-World Scenarios. Welcome, everyone. Let's begin our lesson on a topic that is incredibly relevant to both your everyday decisions and the professional world. Think about your daily life for a moment. Whether you are deciding which route to take to school to save time, or choosing which smartphone to buy based on your budget, you are constantly faced with situations where you need to make the best possible choice among several different options. In the worlds of mathematics and business, we have a specific term for this process of finding that best solution. Whether we are trying to maximize a profit or minimize a cost, we call this process optimization. To help us navigate these complex decisions, we use a powerful mathematical tool known as linear programming, or LP for short. It provides us with a structured way to reach that optimal result. Now, I know that when you hear mathematical tool, you might be expecting a lot of complex formulas right away. However, before we dive into the algebra and the equations, I want us to first understand the why behind this method. To do that, we are going to look at a practical, real-world business scenario involving a furniture dealer to see how these mathematical principles actually work in practice. The scenario, the furniture dealer's dilemma. Now that we understand the concept of optimization from our previous slide, let's apply it to a concrete situation. Imagine you are a furniture dealer. Your business involves selling two specific types of products, tables and chairs. Your primary goal, much like any business owner, is to decide exactly how many tables and how many chairs you should stock in your shop to achieve the maximum possible profit. However, as we discussed in the introduction, we can't just pick any number we want. We are faced with real-world limitations, which in mathematics we call constraints. In this specific scenario, the dealer is facing two primary constraints. First, there is capital, or your investment budget. You only have a limited amount of money available to purchase your stock. Second, there is storage space. Your shop isn't infinite. You have a limited amount of floor space to display and keep your furniture. As we move to the next slide, we are going to look at the specific numbers for these costs and space requirements to see how these constraints actually impact our decision-making. Step-by-step analysis of the problem. Now that we have established the dilemma our furniture dealer is facing, let's move from the concept to the actual numbers. To understand exactly how these constraints, our budget and our floor space, will limit our choices, let us look at the following hypothetical data. First, let's look at the resource requirements and the profit per unit for each item. For a single table, it requires an investment of $500, occupies 5 square feet of space, and yields a profit of $200. Now, looking at the chair, it is a bit cheaper and smaller. It requires an investment of $200, occupies 2 square feet of space, and yields a profit of $100. Next, we must keep in mind our total available resources, which act as our boundaries. The dealer has a total investment capacity of $10,000 and a total storage space of 100 square feet. Keep these specific numbers in mind, because in the next slide, we are going to use them to test out different strategies to see which one brings in the most money. Evaluating different investment strategies. Now that we have our data from the previous slide, let's put it into practice. To see how our constraints actually limit our choices, we are going to evaluate 3 different business strategies. First, let's look at strategy A, where the dealer decides to stock only tables. If we look at our investment constraint, we take our total budget of $10,000 and divide it by the $500 required per table, which gives us a maximum of 20 tables. Now, let's check our space constraint. We take our 100 square feet of available space and divide it by the 5 square feet each table occupies, which also gives us 20 tables. Since both constraints allow for 20 units, we can proceed with this amount. Multiplying 20 tables by the $200 profit per unit, we get a total profit of $4,000. Next, let's consider strategy B, where the dealer stocks only chairs. Using our investment limit, we divide $10,000 by the $200 needed per chair, which allows for 50 chairs. Checking the space constraint, we divide our 100 square feet by the 2 square feet required per chair, which also results in 50 chairs. In this scenario, 50 chairs multiplied by the $100 profit per unit results in a total profit of $5,000. Notice that, so far, Strategy B is performing better than Strategy A. Finally, let's test Strategy C, which is a mixed combination. Let's say we decide to stock 10 tables and 20 chairs. First, we must verify if this is even possible within our limits. For investment, 10 tables at $500 each plus 20 chairs at $200 each equals $5,000 plus $4,000, totaling $9,000. This is within our $10,000 limit. Next, for space, 10 tables at 5 square feet each plus 20 chairs at 2 square feet each equals 50 square feet plus 40 square feet, totaling 90 square feet. This is also within our 100 square foot limit. Now, let's calculate the profit. 10 tables at $200 each plus 20 chairs at $100 each gives us $2,000 plus $2,000, resulting in a total profit of $4,000. As you can see from these three examples, different combinations yield different profits. This leads us to a very important question, which we will explore in the next slide. How can we find the absolute best strategy without having to manually test every single possible combination? The need for a systematic method. Now, let's take a moment to reflect on the three strategies we just calculated. As you can see from our results, different combinations of tables and chairs lead to very different profit outcomes. In our specific example, Strategy B, where we only stocked chairs, yielded a higher profit than Strategy A or Strategy C. However, we must realize that we've only looked at a tiny fraction of the possibilities. There could be thousands of other combinations, such as 12 tables and 15 chairs, that we haven't even tested yet. In a real-world business environment, the situation is rarely this simple. Constraints are often much more complex, and instead of just two products, a company might be managing hundreds of different items simultaneously. Because of this, it is practically impossible to sit down and manually calculate every single possible combination to find the absolute maximum profit. This is exactly why we need a more powerful tool. This is where linear programming comes in. It provides us with a systematic mathematical framework that takes the guesswork out of the equation. Instead of trial and error, linear programming allows us to first, represent our constraints, like our budget and storage space, as linear inequalities. Second, represent our ultimate goal, our profit, as a linear function. And finally, it allows us to use specific graphical or algebraic methods to pinpoint the exact combination of variables that results in what we call the optimal solution. In our case, that would be the perfect balance of tables and chairs to ensure the highest possible profit. Key takeaways. First, we have optimization. You might have noticed in our previous examples that we were searching for the best result. In mathematics, optimization is simply the formal process of finding either the maximum value, like our maximum profit, or the minimum value, such as minimizing costs or time. Second, let's talk about constraints. Throughout our scenario, the dealer couldn't just buy infinite furniture because of limitations like capital and storage space. In any problem, constraints are the specific restrictions or boundaries that limit your possible choices. Every solution we find must respect these boundaries. Third, we have decision variables. These are the unknown quantities that we are actually trying to solve for. In our furniture example, the decision variables were the number of tables and the number of chairs we decided to stock. They are the levers you can move to change your outcome. Finally, we have the objective function. This is the mathematical expression of your ultimate goal. If your goal is to make as much money as possible, your objective function is the formula for total profit. It is the specific equation that we are trying to optimize. Now that we have walked through the furniture dealer's dilemma and seen how different strategies lead to different profit outcomes, let's pause and formalize the vocabulary we've been using. It is crucial to master these 4 key terms, as they form the foundation of every linear programming problem you will encounter. Understanding these 4 pillars will allow us to move from simple word problems to the systematic mathematical framework we will discuss in the next part of our lesson. Common mistakes to avoid. Now, before we wrap up our session, I want to highlight some common pitfalls that students often encounter when they first start working with linear programming. Paying attention to these will save you a lot of frustration in your upcoming assignments. First, be very careful about ignoring your constraints. It is very tempting to look only at the objective function, the part where we want to maximize profit, and forget about the limitations we discussed earlier, like the investment budget or the available storage space. Remember, a solution is only valid if it satisfies every single constraint simultaneously. If you find a combination of tables and chairs that generates a massive profit but requires more square footage than the shop actually has, that is what we call an infeasible solution. In mathematics, infeasible simply means it's not a possible or valid answer within the rules of the problem. Second, try not to fall into the trap of assuming only extreme options will work. In our earlier examples, we looked at strategy A, which was only tables, and strategy B, which was only chairs. While one of those happened to be quite profitable in our specific scenario, you cannot assume the best answer is always to pick just one product. In many complex linear programming problems, the absolute best, or optimal, solution is actually a specific, carefully calculated mix of both products. Finally, always, and I mean always, read the problem statement with extreme care to avoid confusing maximum and minimum. The entire goal of the process depends on this. You need to identify whether the problem is asking you to maximize something, such as profit or efficiency, or if it is asking you to minimize something, such as cost, time, or waste. Mixing these 2 up will lead you to the exact opposite of the intended result. Keep these points in mind, and you will be well on your way to mastering the fundamentals of optimization.